Our first attempt at adding boxes to Mo used Shplait state to implement Mo's state. But this turns out to be an inessential use of Shplait state. You need to use state in your language when you don't control all the channels of communication. But we're implementing interp and everything about interp ourselves, so we can control all the channels of communication, and we just need to make sure that we communicate the information that's needed. What is that information? Well, when we evaluate an expression like box of 7, we need to communicate that whatever memory started out as, the box of 7 allocation step changes memory so that there's a 7 in some cell of the box. So maybe this is cell 13 if we start by numbering from 0. Or if our Mo program has a set box, we need to communicate to all the interpretation afterward that no matter what the value was of that box before, it is now changed to 10, and that if you unbox that particular location of memory, you should get a 10 back instead of a 7. Now, what do I mean again by communication? I mean that we pass information into interp as arguments, and we get information from interp back as a result. In particular, we need to know what is the current state of memory so that if interp needs to unbox at this point in memory, it knows what the current value is. In other words, memory, or some representation of memory, needs to go in as an argument to interp. That means that our interp function, instead of having the type expression environment to value, it needs an extra argument here, which we'll call store. So a store is going to be the type that we use to mean the representation of the current state of memory. Now, what if the expression that we evaluate is a set box? We need not only the store to come in as an argument to interp, but a set box changes the picture of memory, so that means a store must also come out as the result of interp. And a function in Shplait can only return one thing. In addition to the memory, we still care about the value in case it's a plus or something like that. So in order to return two things, both a value and a store, we're going to introduce a new type called result that'll put those two things together. That is, we'll introduce the type result, which has one variant res. Res's only job is to combine a value along with a store so that we can return those two things as one result. Let's see how this change to interp will affect the way we use it. So we used to have num plus with two calls to interp. This worked because num plus wanted two values, which it would check whether they were entities, and each call to interp returns a value. But our calls to interp work differently now. So let's break this up into a sequence. We're going to interpret the left-hand side, then interpret the right-hand side, then add up the numbers we get from those two parts. But when we call interp the first time, now we need to pass in the store. So there's some picture of memory right now. We interpret the left-hand side expression. Often that left-hand side expression just returns a number and leaves memory alone, but potentially it's a more complicated left-hand side that does a set box along the way. So that's why interp is returning us this new store along with this value that we expect to be an integer. The same thing happens with interpar. We need to give it the current picture of memory, which is not the one from before L, but after L. So we take this store that we get back from interp of L and we pass it in for interp of R. The same thing happens here. Interp of R should mainly give us an integer back, but it's possible that it changes the store along the way, that it performs a set box along the way. So we need to see any of those changes. That needs to be communicated out to us. Now when we actually add the numbers, we only need these two results. We don't need the store. But then after we've added the numbers and we want to return it from interp, we need to return that store as well. That is, we're going to have to build a res to return the added numbers along with this current store. Meanwhile, the two numbers that we got back from interpol and interpar, that is what went to num plus. So we have this flow of values that we need to turn into some code, and that looks like this. Right? We call interp of L and env. I'm going to call stow the new argument to interp. That's our initial store here. When we call interp, we get back a result. That is a res, but will have some value for the left and some store for the left. We use that store for the left when we interpret R. And then we get a value for R and a store after R. And this store after R, this one right here, that's the one we return as the result. Meanwhile, we can add VL and VR as before. Those are the two values that we expect to be integer values. I haven't yet said how we are representing this store though. So the data type capital S store is going to be a list of storage. Each storage corresponds to one of those boxes in the picture. So it's a particular cell, each cell is at a location, and each cell has a value inside of it. And the location we'll just use a number for. So it corresponds to the address in memory, if you will. We'll count from 0, 1, 2, 3, 4, 5. Those will be our addresses in memory. Each address in memory is mapped to a particular value as a storage. This is analogous to a bind in the environment, and we'll have a list of storage to get a store, analogous to a list of binds to get an environment. We need an empty store because that's how we start out. Nothing is allocated at any location in memory, and we'll also define override store as an alias for cons, very much in the same way we defined extend env to be an alias for cons for environments. So, for example, if we want to represent this picture of memory, here the only thing I have in memory is this 10 allocated at box number 13, right? 0, 1, 2, 3, and so on gets you to 13. So that is 13 mapped to the int v10. Okay, we have to put a capital V value there. We make that cell, we add that cell to the empty store using override store. This Shplait expression represents this picture of memory. If we have two cells allocated in memory, then that means we'll be using override store twice. Once for cell 1 in this case, and then for cell 13.